All right, everyone, thanks for coming. So today, we're going to dig into something that's, well, it's one of the absolute cornerstones of building high-performance systems, resource pooling. We're going to start right at the beginning with the core ideas and then work our way all the way up to the best practices that you can literally go and apply after this session.
So before we jump in, just a quick heads up. I use some AI assistants to help me distill a whole mountain of source material into this deck. I just want to be transparent about that. This isn't AI-generated slop. It's about using a tool to get us to the important stuff, the core engineering principles, a lot faster. And that's really what we're all here for. Okay, let's get to it.
So here's our roadmap for today. We're going to start with the why, the fundamental trade-off that makes pooling a thing in the first place. Then, we'll dive into the two big use cases: thread pools for chewing through computation, and connection pools for dealing with I/O. After that, we hit the big one, the sizing dilemma. Then we'll look at all the ways this can go wrong with common anti-patterns, and wrap up with a little peek into the future of pooling.
So, first up, the fundamental trade-off. At its heart, every single conversation about resource pooling boils down to this one classic engineering decision. Are we going to spend time, or are we going to spend space?
And that immediately raises the question, right? Why is it so expensive to just create a new resource whenever we need one? Why not just spin one up on demand? Well, because creating things costs. It costs CPU cycles to create complex objects, it costs significant OS-level overhead and memory to spin up a new thread, and, maybe most importantly, it costs a ton of network latency to establish a new connection. All of that adds up to a huge performance hit if you're doing it over and over again.
In this slide, this is the whole game. This is the key. What pooling does, really, is it takes that temporal cost, the time, the latency, the CPU burn of creating something from scratch for every request, and it converts it into a spatial cost. We are making a conscious decision to spend a little bit of memory, a bit of space, to keep a bunch of these resources warmed up and ready to go in a pool. Think of it like prepaying a toll. You pay a little up front so you can fly through the gate when you're in a hurry. You have to get this mental model down because everything else we're going to talk about builds on this one simple idea.
Okay, so let's get into our first major application of this idea and see how it works in practice, managing all of our computational work with thread pools.
So, what is a thread pool? Well, it's pretty much exactly what it sounds like. It's a managed collection, a pool, of worker threads that we create ahead of time. And the whole point, the entire reason for its existence, is to avoid paying that incredibly high overhead of asking the operating system for a brand new thread every single time a task comes in. We create them once at the beginning, and then we just reuse them, over and over again.
Now, what's cool about this slide is that this four-stage life cycle, it applies to any kind of pooled resource, not just threads. A really great analogy is a library. Step 1, the library buys the books. That's creation. Step 2, you go and check a book out. That's borrowing. Step 3, you take it home and read it. That's usage. And step 4, and this is absolutely critical, you return it. The pool then has to sanitize it, make sure it's in good condition for the next person. This last step is so important for preventing state from one operation from leaking into the next.
So what happens when all the books are checked out, when the pool is empty? This is a huge architectural decision you have to make. Do you fail fast? Just immediately tell the client, sorry, we're all out, try again later. Or do you grow on demand? Basically, create a new resource on the fly, as long as you're under some maximum limit. Or do you make the client block and wait? Force them to stand in line, hoping that somebody returns a resource soon. How you answer this question completely defines how your system behaves when it's under heavy load.
Okay, so that's how we handle computation. Now let's switch gears and talk about the other side of the coin, which, frankly, is often even more critical, managing I/O with connection pools.
And listen, if you thought creating a thread was expensive, trying to establish a new database connection is on a whole different level of slow. It's not just one thing, it's this whole waterfall of slow operations. First, you've got DNS resolution, then a full network round trip for the TCP handshake. Then, if you're using security, which you should be, that's another 1 or 2 round trips just for the TLS negotiation. And only then can you finally send your credentials and get authenticated. Trying to do this for every single request in a high-traffic app, it's a non-starter.
Okay, so this is super important. Once we've paid that high price to get these connections, we have to make sure they stay healthy while they're sitting in the pool. A connection can go stale. Maybe a firewall in the middle just silently dropped it, or the database server restarted. Connection validation is our health check.
It's a tiny, super-fast query, something like select one, that the pool runs on a connection right before it hands it over to your application. Without this, the pool could hand you a dead line, causing your application to just hang and eventually time out with a nasty error.
All right, this brings us to what is often the hardest part of this whole thing in the real world, the sizing dilemma. How in the world do you figure out how big to make these pools?
Well, the good news is, for I/O-bound tasks, like waiting on that database, we don't have to just guess. We can start with a really powerful heuristic, which was famously laid out in the book Java Concurrency in Practice. The core insight here is that it's not just about how many CPU cores you have. It's about the ratio of time a thread spends just waiting for I/O versus the time it spends actually doing work on the CPU. The goal is to have just enough threads so that while one is blocked waiting for the network, another one can be using the CPU. It's all about keeping that CPU busy.
And this table just makes that distinction crystal clear. If your workload is CPU-bound, I'm talking raw number crunching, then your optimal pool size is simply the number of cores you have. Any more than that, and you're just creating wasteful context switching for the OS. But if your workload is I/O-bound, where threads spend most of their time just waiting around, you can and should have significantly more threads than cores. Figuring out which bucket your workload falls into is probably the single most important factor for tuning your pools correctly.
Okay, so we've got the theory, we've got the patterns. Now let's talk about the fun stuff, the anti-patterns. These are the common ways that this powerful optimization can go horribly wrong and actually kill your system. I really want you to burn this quote into your memory. When you see pool exhaustion errors lighting up your dashboards, your first gut reaction is going to be, just make the pool bigger. Don't. Please. Just don't do it. Pool exhaustion is almost always a symptom. The real root cause is probably a slow database query or maybe a connection leak somewhere in your code. If you just increase the pool size, you're not fixing anything. You're just hiding the problem, and worse, you're probably about to create a death spiral by throwing even more load at your already struggling database. And yeah, just to hammer that point home, this idea that a bigger pool is always better isn't just naive, it's actively dangerous. An oversized pool doesn't just waste a bunch of memory, it can completely overwhelm your downstream systems. Just picture it. You have 200 threads in your application pool, all trying to hammer a database that can only really handle 50 concurrent queries. Your performance won't get better, it will grind to a halt for everyone.
And there are other classic ways to shoot yourself in the foot. Connection leaks. That's when you borrow a resource and forget to return it, slowly bleeding your pool dry. Ignoring network timeouts. This happens when your pool's idle timeout is set way higher than, say, a firewall's timeout, which means you end up with a pool full of dead connections. And of course the classic one-size-fits-all approach, where you just copy-paste the same pool configuration everywhere for services that have totally different needs. Every pool needs to be tuned for its specific job.
So, where is all of this going? Let's wrap up by taking a quick look at what the future holds for pooling and concurrency in general.
What's really fascinating is this huge paradigm shift that's happening with things like virtual threads in Java's project Loom. The goal here is basically to give us the best of both worlds. We get to write simple, easy-to-read code as if we have a new thread for every request, but we get the incredible performance of a shared pool running underneath. The language runtime itself handles all the complexity of scheduling millions of these lightweight virtual threads onto a small pool of actual OS threads. It's essentially pooling, but it's automated and hidden away from us, developers.
And that leads us to one final kind of provocative question to think about. As our runtimes get smarter and smarter with things like virtual threads, is the whole art of manually configuring and tuning resource pools, is it becoming an architectural relic? Is this entire session something we won't even need to talk about in 5 years? Something to chew on. Thanks, everyone.